Hello everyone, welcome you all on our channel eFunda for new day, new topic, and today's topic is Temperature Engineering Guide Part 9. In this topic, we are going to cover various types of temperature measurement scales and their measuring instrument. So if you are new to our channel, please watch our complete engineering series which we have created specifically on the technical subject, and don't forget to subscribe to our channel to get latest updates and reviews on various subjects. So let's begin with our today's topic, that is temperature engineering guide. Temperature is the degree of a hotness or a coldness, a measure of a heat intensity or amount measured in terms of degree Celsius or degree Fahrenheit. The most common symbol or abbreviation for temperature is a capital T. Temperature is a measuring unit for heat and expressed in various types of measuring unit, that is degree Celsius, degree Fahrenheit, degree Kelvin, degree Rankine, and Reaumur. One can see in a below table where we have defined all the scales are available for measurement, and in another figure we have seen the thermometer and their respective conversion in respective units. Here we will see through the table. Freezing point of a water is at 0 degree Celsius, Fahrenheit is 32 degree Celsius, Kelvin is a 273.15 degree Kelvin, and Rankine is 491.67 R. Boiling point of a water is 100 degree Celsius, and so that equivalent conversions are also given. Absolute zero is a minus 273.50 degrees Celsius, and subsequent conversions are also defined in the table. For these conversion, one can refer to the conversion formulas given. With this, you can understand how the different types of temperature measuring scales will be converted to the another type of a scale. So these formulas one must remember and try to solve various kind of example so that you can understand the conversion easily. Temperature measurement can be achieved by using the following temperature sensors: thermocouples, TC, resistance temperature detector, that is RTD, Thermo Well, that is TW, thermistor, bimetallic thermometer, field thermal system, pyrometer. These are the few key temperature measuring sensors. The selection of these instruments can be better judged by the engineer who is involved in the detail engineering phase, as working engineer knows the exact requirement of temperature measuring ranges and their application with respect to project scope. Thermocouple. A thermocouple is a sensor for measuring temperature. It consists of two dissimilar metal joined together at one end, which produce a small unique voltage at a given temperature. One can see in a below figure where measuring junction and a reference junction, that is hot and cold junctions, are shown, where heat source is provided and a cold junction is also there. One can see the difference between two measured in a voltmeter. The thermocouple output is in millivolt, and this voltage is measured and interpreted by a thermocouple thermometer. One can see in animation, as soon as the temperature or heat is given to the hot junction, it created the difference in the temperature, and same can be shown on the dial type thermometer. Similarly, there are various types of effects are involved. Seebeck effect, the voltage or electromotive force, that is EMF, induced by the temperature difference, that is a gradient, along the wire. The change in the material EMF with respect to change in temperature is called the Seebeck coefficient or thermoelectric sensitivity. This coefficient is usually non-linear function of a temperature. One can see in a figure that Seebeck effect, that is the animation. You can see how the movements are being taken place. The Peltier effect, describes the temperature difference generated by EMF and is reverse of the Seebeck effect. Finally, the Thompson effect relates the reversible thermal gradient and EMF in a homogeneous conductor. One can see in below animation. This is how the thermocouple works. Thermocouple construction. Thermocouples are usually protected by placing them into a metal sheath, usually made of stainless steel. The conductors are then mineral insulated, usually with magnesium oxide powder. One can see below there are various types of configuration. There is a grounded junction thermocouple, ungrounded junction thermocouple, and exposed junction thermocouple. In a grounded junction, thermocouple element is attached to the probe. Ungrounded, the thermocouple element is detached from the probe wall. And exposed junction, that is a thermocouple junction, protrudes outside the probe sheath. This is how the construction of this Thermowell. Normally element is placed in a Thermowell. Commonly element is quarter-inch outside diameter, that is OD. Sheath material normally stainless steel, but can be special material such as Inconel, Incolloy, Hastolloy, etc. Depends on the application and client specification. Duplex thermocouples have two elements inside one sheath. One can see in a figure arc welded junctions and conductor insulated magnesium oxide powder. Sheath normally stainless steel, and the complete thermocouple assembly one can see in a last figure. Basically, various types of thermocouples are required for temperature measurement, and typical thermocouple types are shown in a comparison table where one can find thermocouple type, conductors, temperature ranges, as well as their Seebeck coefficient and application environment. Typically, various types of thermocouple E, J, T, K, N, B, S, R. These are the main types available for this thermocouple, where one can see the configuration, that is a K type. K type is defined as a chromel and alumel. Chromel is a positive side and alumel is a negative. One can see in a figure where K type is defined, that is in yellow color, that is a chromel, and red is alumel. This is how the thermocouple type K is defined, and the lead wires one can see below this figure. Thermocouple temperature compensation, there is cold junction and a reference junction. Cold junction, the basic principle behind cold junction compensation is that you must know the cold junction temperature to calculate the hot junction temperature. This is because the voltage generated in a thermocouple circuit is proportional to the terminal difference between hot and cold junction. One can see in a figure where T1 is a hot end and TCG is the cold junction compensations, that is the cold junctions are provided where thermocouple material 1 and 2 are defined and voltmeter is connected. And to get the cold junction compensation, one should know the exact value of this junction temperature. One can see in a figure that similarly this cold junction compensation is done through the ice water, that is a 0 degree Celsius, where we have defined the temperature of this ice water and hot junction is also connected. This is how the compensation is achieved in the thermocouple. Moving on to Rtd, that is resistance temperature detector. They operate on the principle that resistivity of a metal increases in proportion to its temperature. In other words, as the temperature of a metal increases, so does the resistance to the flow of electricity. An electrical current is passed through the sensor. The resistance element is used to measure the resistance of the current being passed through it. Typical Rtd can be seen in below figure, where one can see connection head, RTD lead seal, terminal blocks, removable retainer, spring loaded mounting fitting, RTD probe sheath, insulated leads package in MGO, RTD sensing element subassembly, and outside this Thermowell where the RTD is placed inside the Thermowell. In another figure one can see how the components are being placed and details of each component is indicated. Lead wire, process connection, 3-wire configuration, OD that is outside diameter, platinum resistance element. This is how the RTD look like and their typical constructions. Typically, three types of RTDs are commonly used in industrial application. Wire wound RTD elements comprise a metal wire, usually platinum, but also copper or a nickel, wrapped around a glass or a ceramic bobbin and sealed with glass. Partially supported wound RTD element are produced with a small coil of a wire inserted and attached to one side of the hole in the ceramic insulator. In a thin film RTD element, a thin layer of a platinum or metal glass slurry is deposited onto a ceramic substrate. These sensors offer most accuracy and the longest lifetime but are typically more expensive than other two types available in the market. Typically PT100, that is a resistance value at a 0 degree is 100 ohm, that is called PT100, has been popular worldwide because of good temperature characteristics, is linear and stable. There are various types of wire connections, that is 2-wire, 3-wire RTD and 4 wires. One can see in a figure how the configurations are defined, and a last picture one can see typically RTD types and how the RTD look like for better understanding of their construction. Moving on to Thermowell, a temperature element cannot be placed directly into the media which is to measure. In this instance, a TW must be used to protect a temperature element. Thermowell are cylindrical fitting used to protect temperature sensor installed in industrial processes. One can see the typical PNID representation for the temperature measuring device installation where only TT is shown. While designing the temperature loop, one must understand that Thermowell is additionally required to protect the element of those sensors, and T is also required to have the transmitted output, that is in terms of 4 to 20 milliamps. So whenever in the PNID if TT is only shown, then one should always have a component that is a TW Thermowell and temperature element, either it may be RTD or a thermocouple, and then it's connected to the transmitter. This is how the typically PNID representation. Thermowell insertion lane shall be in the middle third of a pipeline size for better result. One can see in a figure where Thermowell is installed between middle third of the pipe diameter. Here to find the exact length of the Thermowell, wake frequency calculation is performed, that is based on ANSI PTC 19.3, where the latest edition says wake frequency ratio should be less than 0.4. With this one can say that the Thermowells are passing and it will not broke during the vibration while the fluid movement through the pipe. Most Thermowell in a process and a petrochemical industries are formed out of either material that is stainless steel or other alloys or ceramic metals. For examples, SS304, SS316, SS316L, SS310, Inconel 600, Incolloy 800, Monel and Hastoloi. This is how these materials are used in a industry based on their application and the requirement. Types of Thermowell and their selection. one can see how the Thermowell is look like, and the various types are available, that is a threaded, flange and welded. These are the most commonly used, and their construction types are tapered, straight and stepped. While selecting the complete Thermowell design, one should understand the questions, that is the type of connection to the process required, best material of a construction for your need of application, best temp profile for your need of your application. This is all about the temperature measurement, their sensors and protecting element Thermowell. With this, we are concluding on today's topic, that is a temperature engineering guide, and hope this video will provide you the valuable sharing of technical information. If you are new to our channel, then please subscribe to our channel to get latest updates and reviews on various subjects. Keep watching our channel eFunda. Stay tuned for new topic, new day.